Hello everyone, welcome back to our course, the Construction 3D Printing Techniques. Today we are looking into parametric 3D modeling for the nonlinear object that you want to print. Parametric modeling, design, and optimization stand at the forefront of innovation in 3D printing in general, offering a transformative approach to architectural and structural design with many nonlinear features like undulated curve with incredible designs. As the name implies, there will be an involvement of parameters and the relationship between those parameters. In other words, mathematical equation, or sometimes also known as algorithms. Depending on the number of parameters and the mathematical equations that you use, the possibility that you can create will be countless and enormous and super creative. If I give you a definition of parameter modeling again, the parameter modeling refers to this detailed design approach where objects are created and manipulated using parameters or variables, but normally done in a software environment where there are already a bunch of nice mathematical equations available for the parametric design and helps end users easily create their own objective without much understanding of the math behind. These parameters are interconnected, allowing changes to one parameter to another dynamically and influence and modify the entire model. It involves using algorithms, rules, and the relationship between elements to create dynamic and adaptable designs. The interconnected parameters are allowing changes in one aspect to dynamically affect the entire model. And thanks to today's high computing power, they're reflecting the changes almost in real time. For instance, by altering the parameters related to shape, size, or density, designers can instantaneously witness how these modifications impact the structural integrity, aesthetics, and functionality of the final printed elements. Algorithms and rule-based systems lie at the core of parametric modeling. These computational tools enable designers to define rules and constraints that guide the behavior of and interaction of different design elements. By establishing these rules, designers can automate the generation of complex geometries and adjust the designs based on various inputs, such as load conditions, material properties, or aesthetic preferences. Parametric modeling also facilitates an iterative design process by allowing designers to swiftly explore an extensive range of design variations. Through this iterative approach, designers can experiment with different parameters, refining and optimizing design iteratively. This rapid iteration enables the exploration of innovative design solutions that meet specific performance criteria and respond to evolving project requirements. Parametric models in 3D printing in general are not just aesthetical representations. They possess predictive and capability that simulate materials behavior and forecast structural performance. By integrating materials properties, flow behavior, and printing constraints into the parametric model, these designers can anticipate how the design alteration might impact the printed object's behavior and performance. Manipulating variables within the parametric model, such as the shape and size and thickness or density or things like that, allows designers to exert the precise control of the structural and aesthetic attributes of the final printed elements. This control extends to optimizing designs based on specific performance criteria, such as the load-bearing capacity, structural stability, or even visual appeal. I can now give you a quick demonstration with a very simple and fundamental parametric modeling design to make you more understood and also the refreshed. So now here, you can see there are three parameters called A, B, and theta. Currently, A and B are set to 1 and theta is 0. If I make a change of A to 2, boom, Let me change the parameter b to 2. Then it returns back to slanted straight line. If I change b to 3, then you will get another different shape, which is closed loop shape. Let me make a to 5 and b to 8. And here it is. Similar closed loop shape, but more tangled, right? Now it's time to change theta. You'll get the point as I gradually change the theta. This is called a Lissajous curve, named after Jules Antoine Lissajous. It's a curve of the following two parametric equations. X equals capital A times sine AT plus like a theta, and Y equals to capital B times the sine of BT. The capital A and B represent amplitude in the X and Y directions, and A and B are constants, and theta is a phase angle. This is one-top parametric design in two-dimensional using sinusoidal equations. You could make more complicated, and you can even make it three-dimensional. As you go for more complexity, you'll likely need a dedicated software for the parametric designs like Rhinoceros 3D, Autodesk Inventor, or Fusion 360, SketchUp, and so on. I'll leave the link below, and then you can actually do some experiments of yourself. Now you should have a better understanding of what parametric modeling, design, and optimizations are. As mentioned earlier, this is extensively used for many applications. Here are possible 4 different optimization approaches often considered. The first one is design optimization. This aspect involves utilizing computational techniques to refine designs and aiming to achieve predetermined performance objective while navigating multiple design constraints. Through optimization algorithms, designers can identify the most efficient and robust design solutions. The second one is topology optimization, or sometimes called topological optimization. This method focuses on optimizing the distribution of material within a defined design space. By minimizing unnecessary material usage while ensuring structural strength, topology optimization plays a critical role in 3D concrete printing or 3D printing in general. It helps create elements that use material precisely where needed, reducing excess material in non-critical areas without much compromisation of the performance of the structure. Third point is form finding algorithms. These algorithms help in discovering optimal structural forms considering specific constraints by iteratively exploring various structural configurations. Form finding algorithms optimize the material utilization and structural performance. This approach often leads to innovative and efficient designs in 3D printing. Number 4 is performance-based design. This optimization considers various performance criteria such as load-bearing capacity, stress distribution, efficiency in material utilization, and sustainability aspects. By integrating these parameters into the design process, designers can craft structures that not only meet specific performance standards, but also minimize material wastage, or ones can make the structure's performance greatest with a given constraint. All right, here we are. We've explored the profound impact and use of parametric modeling, design optimization today. Actually, today's class is more for the general 3D printing and 3D modeling, not only for 3D concrete printing. With such techniques, we can witness a paradigm shift in architectural innovation if applied correctly in 3D concrete printing. Indeed, these methodologies redefine the way structures are conceived, designed, and brought to life, offering a systematic and data-driven approach. With a newfound ability to craft intricate design, minimize material wastage, and swiftly iterate through concepts, this transformative approach not only redefines architectural boundaries, but also champions a more sustainable future for construction practices. Please stay closer for the following video, as I'm going to discuss the actual softwares you can use for modeling, slicing, and run 3D printers. Stay excited and see you in the next class. Bye for now.